Bismillahirrahmanirrahim. Assalamualaikum. Selamat Hari Raya to some of you or to all. And good morning. Today we will cover the topic on frequency response techniques. It's covered in chapter 15, 16 of your book. And basically some of it you have seen it before, but only in a different form. Now it's in the form of a frequency response. So far we have looked into time domain. Now we look into frequency response, why we are using it. We'll see later. Got so many useful things that we can learn from this. Okay, if you look at the first order system given by the standard gain and time constant, if you over tau s plus 1, and if this is in basically in from time domain, which is in ODE, we convert into Laplace domain. And to convert Laplace into frequency domain, basically we just convert or change, substitute S with J omega, which is the frequency of the system. So basically, by doing that, basically we are going into the frequency domain technique. And in this case, when we substitute S equals J omega, then we will get Kp over tau J omega plus 1. And if we convert into the conjugate part, the real part, and the imaginary part, then we'll get it basically a system where it has an amplitude ratio of Kp over square 1 plus omega squared tau squared and a phase angle of 10 minus 1 minus omega t. How do you get that? You get by this. This is in the real domain. This is in the imaginary domain. So you get the magnitude of this what you call a vector vector system. And basically the magnitude is given by square root of the real part squared plus the imaginary part squared, which is given by Kp over 1 plus omega tau squared, which is this. So this is the amplitude ratio for the first order system, and the phase angle is just 10 minus 1 of the imaginary part over the real part, and basically 10 minus 1 minus omega tau. So this is basically converting into the frequency domain by just substituting S equals to J omega. And in the frequency domain, what we're interested is basically the amplitude ratio and the phase angle that it subtends. And basically, where is it coming from? This is basically coming from frequency response, coming from when you input sinusoidal into your first order system. And we have seen this before. We've seen this, we'll show that later. So the magnitude and phase angle is the amplitude ratio AR and phase angle obtained when the system has input with the same sinusoidal wave frequency. Then you put a sinusoidal wave frequency, the output that you're going to get is going to be the AR and phase angle. It's changed with frequency. They are changing with frequency, of course. And we have seen this in chapter 4. When you put a sinusoidal input into the first order system, this is the output you're going to get. If you just take basically remove the transient part, you just take the final steady state part, this is what you're going to get, the output, which is given by the amplitude ratio and the phase angle lag. And this is what we got just now. By substituting J equals to S omega, you get the amplitude ratio AR as the magnitude and the phase angle here, which is given by 10 minus 1 omega t. Same thing. Also, basically, the output is a sine wave with frequency omega equal to that of the input signal, and the ratio of the amplitude output amplitude to input amplitude is this one. This is the AR amplitude ratio we called just now. Smaller than 1 because it's a signal is attenuated, which is normally for first order system, and the output lags behind the input by the angle phi, which is negative, which means it's lagging. If it's negative, it's lag. If it's positive, means phase lead is leading. So this is the first order system that we've seen before, the amplitude ratio and the phase angle, and this is basically the frequency response part of the whole first order system and all others that we will see later. And so we can do the same thing in order system. This was the transfer function given in terms of S domain. We want to convert into the phase angle and amplitude ratio, which is a frequency response domain. So just convert S equals J omega, we'll get this transfer function. We want to get amplitude ratio and the phase lag, we have to convert into the conjugate the real parts and the imaginary parts by just multiplying by the conjugate, which is minus 1 minus tau squared omega squared minus 2 zeta tau omega j over 1 minus tau squared omega squared minus 2j tau zeta tau omega. You will get this real part and the imaginary part. From the real part, imaginary part, we can get amplitude ratio, the imaginary part squared plus the real part squared, and this is the amplitude ratio for the second order system. The phase angle is again given by the imaginary over 10 minus 1 imaginary part over the real part, which is given by this. This is what we got again from what we've seen before for the dynamics of the second order system. If we put a sinusoidal input into the second order system, this is what we get when we look at the previous chapters on page 152 of the book. This was the output that we got looking at the final part, removing the transient part, taking the final steady state part. This is what we are going to get, and this is basically the amplitude ratio, which is given by the output amplitude over the input amplitude. And this is amplitude ratio, and this is the phase lag. And the phase lag is equal to minus 10 minus 1, this minus zeta omega tau over 1 minus omega tau squared, which is what we got just now by substituting s equals j omega, and the amplitude ratio is given by this is what we got when we go s equals j omega and get the amplitude ratio. So basically, what we're trying to say when we want to get the phase frequency response, basically we change s equals to j omega, and in other words, it's also the same as getting the output of a sinusoidal input system going into a second order system. What is the output? The output is given in terms of the amplitude ratio and the phase angle, and that is what it means by frequency response. Is when we are dealing with output related to frequency response, dealing with omega, the frequency. How you get frequency? When you put a sinusoidal system with frequency put into any order system, we're going to get an output which also gives you some frequency depending on first order, second order, and so on. And this it gives in this form for second order and for the phase lag and so on. So this is the same thing you can do for all other systems. That's what we've done. We're converting from the Laplace transform into sinusoidal to frequency domain, just inputting sinusoidal input system. Same thing here for date time. If you put s equals j omega into date time, you're going to get this transform function. You're going to get this function, and this basically shows that AR equals to 1. Yeah, the magnitude here is the AR, and the phase angle is this part here, minus omega tau d for date time, which is the simplest, but you can prove yourself how why AR equals to 1. You can look into this and convert this into the trigonometry system that will give you the real part and the magic part for exponential system. You can do the same, and you have system in series. This case, first order systems in series, the same thing, you do it separately for s equals j omega, and for the first order for G1, this is the amplitude ratio, and this is the phase lag. For G2, this is the amplitude ratio, this is the phase lag, and so on, so on, so on. So if you want to get the overall amplitude ratio for this transfer function in series and overall amplitude ratio for this transfer function in series, just basically so now we go for the controllers. The controllers, you get GC equals to KC, amplitude ratio equals to KC, and the phase lag is just 0. There's no phase going on here because there's no S transformation here. So it's just a constant. So the amplitude is constant. The phase lag is 0. The PI controller, substitute S equals j omega. You're going to get the amplitude ratio given by this part, and the phase lag is given by this terminal, which is less than 0. For the PD controller, you're going to get the phase amplitude ratio equals to given by this when you substitute s equals j omega, and you're going to get the phase lag given by 10 minus 1 td omega, which is greater than 0. It's called phase lead. Doesn't exist on its own, but basically it's giving phase lead, which means giving stability. Whenever you have phase lead, you get stability. Whenever you have phase lag, you got instability. So we said before, D introduce stability, and this we can see by this, where it introduce phase lag into the system, and you get more stable output. PID is just a combination of the PI and PD, and A amplitude ratio is given by this equation, and the phase lag is given by this. So it can be phase leak or phase lag depending on the individual values, whether it's positive or negative for the phase lag. Negative for phase lag and positive for phase lead, and so on. Okay, so you can do for all the transfer functions, you're going to get all those different amplitude ratio and the phase lag, and you can get basically that is the frequency response for each of the transfer function. But we have to make it more simple, those things, numbers we can't see so clearly. So what has come out is that somebody has designed or come up with the idea of body himself, body diagram, basically a convenient graphical representation of dependence of AR and the phase lag with respect to frequency. Most of them are dependent on frequency most of the time, so you can just plot the AR with frequency and the phase lag with frequency, and you can get the pattern for the system or for the transfer function. So basically, body diagram consists of two graphs: the log amplitude ratio versus log omega is a log graph, log graph. The other one is a phase lag versus log omega, which is a semi-log. This one is not log, it's the phase angle, and this is log omega. Why we use log? A lot of simplicity there. You will see later. We can plot asymptotic plot and so on. So it's got some advantage in using log plot. If you use the actual plot, it takes a bit more longer. It takes a bit more complicated way of calculating. But this one makes it more easier if you use a log or semi-log. And this is the body diagram. And the important parameters to look at when you look at the body diagram. What we have, the low frequency asymptote, the corner frequency high frequency asymptote, and the two curve. The two curve is the actual equation itself, but you can also approximate it by the asymptotic curve for the amplitude ratio. For the phase lag is the same one, but for this one you can get what we call asymptotic body plot. Again, let's look at the first order system, where you have this is the first order system. Okay, and this is simplified first order system kp over tau s plus 1. As we mentioned just now, we put j s equals j omega, then the amplitude ratio equals to this, okay, and the phase angle equals to this. Okay, if you take the log of the amplitude ratio, then you're going to get this equation. Okay, since we are plotting the log plot, so we are looking into the equation after taking the log for the log plot. So what happens? So we are looking into that. We're trying to what we're going to do is to try to plot what we call the asymptotic plot for the body diagram for the log AR versus log omega. So if you look at it, if omega tau tends to 0, then these values, then from here we can see the AR tends to go to 1. Tends to go to 1. Okay, basically R equals to 1 or whatever gain value it goes to. And if omega tends to infinity with a higher value of omega, this is mean low value of omega, this high value of omega, then the equation just now becomes log AR equals to minus log omega tau, and this is a line which has a gradient minus 1, this line. So what it means that this is what we call asymptotic plot. You can plot the low asymptotic line and the high asymptotic line. The low asymptotic moving towards the gain at the small omega values, okay, or the gain of the system, exactly is the gain of the system or small omega, and the high asymptotic plot is the line with the gradient minus 1 or whatever system it is, moving towards the tau equals to infinity. So it's just a line with a gradient. There's the low asymptotic line, high asymptotic line. Where does it cross? It crosses at a value omega tau equals to 1. Okay, and at omega tau 1 means it's called the corner frequency is 1 over tau. So where it crosses at the value 1 over tau. If you know the time constant, then you know where it crosses. The low asymptotic line crosses the high asymptotic line at this point, which is called corner frequency. See, the red one is the asymptotic line, low asymptotic line, high asymptotic, the blue line is the actual curve. We plot the actual curve, that is the blue line. So it corresponds at low values of omega, it corresponds at a higher value of omega. And here there's a slight difference, and the maximum is normally only about 30% this point. This is the highest difference is at this corner frequency, and normally it's about 30%. It's good enough for us to use this for designing many things. And for the phase lag, that's not something, just actual. So, but you can see that when omega is 0, omega is small, it's not 0 going small, then the phase angle is 0. When omega gets to infinity, the phase angle is minus 90. When omega is at the corner frequency omega tau 1, then the phase angle is minus 45. So 0, minus 45, 90. Yeah, the maximum it goes is to 90. For first order, the maximum is at 90 degrees phase lag. Okay, so you can see summary of the body diagram for first order system. You get the true curve. If you plot the actual values without taking the asymptote, you get plot the true curve. If you take the asymptote, the lower frequency asymptote, the high frequency asymptote, cuts at corner frequency, this is what you're going to get, the dotted line, which is slightly different, not much difference. So this is a log plot. So log, you don't have to take the log. When you log, that's why you advantage of using log plot. You just take the values on the log plot without having to take the log. Only thing, the gradient is not calculate normally like we calculate, but the gradient is calculated based on distance. For if you get -1, it's not how you calculate the normal graph, but it's a -1 based on distance for log graph. And phase angle is actual numbers. This is actual, so and this is a log. So it's a log, semi-log, actual versus log graph. But so there's no asymptote here. And these are actual values, and you can also convert to decibels if you want. -20 log 10 of the amplitude ratio, not big issue. You can either plot this one in this normal way, or you can plot in terms of decibels. So this is how you can have a body diagram for first order system, either real curve or asymptotic curve. As I said, the maximum values or difference is given at this corner frequency, which is about 30% difference. Because the value here is 0.7 something, and this one is 1, so the values is only about 30% difference. And for second order system, the same thing. You have the transfer function, you convert into the frequency domain, you get amplitude ratio equals to this, and the phase angle equals to this, have been shown before. And if you want to plot the asymptotic plot, let's look at the values at 0. 0, the AR tends to 1, phase angle 0. And for omega tau tends to infinity, high values, you take the log of the equation just now, and this is what you're going to get. And what does it show? It shows this is a line, asymptote line with gradient -2. If you plot log AR versus log omega, you get a line with gradient -2, and at omega tau infinity, the phase angle is -180 degrees. The maximum it goes is -180 degrees. For second order, it goes to -180 degrees, and so on. For third order, it goes to -270, and so on. Phase lag for second order, maximum -180 degrees. And if you look at the corner frequency, where the low asymptote cuts the high asymptote, and you at the corner frequency, and the corner frequency, the value is at 1/tau, just like first order system. That's where the corner frequency is, and the phase angle at that corner frequency is -90 degrees. So it goes from 0, -90 to -180 degrees for second order body plot, or what they call phase frequency response plot. And if you look at this in summary for second order system, this is the asymptote, the dotted line going to 1 for low frequency, and have a gradient of -2 going to for the high frequency. That's the corner frequency at 1/tau. 1/tau, if you plot the omega tau, is at 1. And of course, second order also depends on the zeta, so you have different plots. Different zetas, you'll have different plots, and but asymptotically it goes to the same values at the asymptotes from here and the gradient here. It's only difference at the middle, and especially at the corner frequency has got maximum change. Well, not so much different. You can use most of it to design your controllers and all. This is good enough. The asymptotic plot is good enough. And the phase angle plot is like that. Again, from 0 goes to -180 degrees, but again, slightly different in between due to the different zetas that is in that affects how the behavior of the system. If you got first order systems in series is the same thing. Just now we said the amplitude ratio is a multiplication of the individual amplitude ratio, and the phase lag is as addition of the phase lag. So what happens is that we take the log is just the log of the amplitude ratio 1 plus log of amplitude ratio 2. We take the phase angle is just phase angle for system 1 plus phase angle of system 2. And basically, if you look at it, example in this case is given in the book. We have two systems here. So what will happen is the amplitude ratio is given by this for system 1 and for system 2. And the overall is just a multiplication of both, which is given by this one. And if you take the log, it is basically adding the log of for the amplitude ratio of system 1 plus the log amplitude ratio of system 2 plus the gain here. You have a gain 1.5. You can add the log 1.5 gain. You can do this, or you can just multiply the y-axis by the gain, and you don't have to worry about this part. Okay, so this is what is happening. You can see here for the first order system. We got two first order systems just now. One of them is 1 over s plus 1, low asymptotic plot, high asymptotic plot, corner frequency at the tau, which is 1. For this transfer function, this is the low asymptotic plot, this is the high asymptotic plot, the greater than minus 1, this one also greater than minus 1. Where is the corner frequency? At the value of 5, because that is the tau. Corner frequency is at 1 over tau, which is at 5. So you got two plots. You take the overall, it's just adding this one plus this one goes low asymptotic plot. At this point it's minus 1, but at this point you got another line here, so you can minus 2 at this point. Minus 2 at the second corner frequency. And how to take care of the 1 over 5, you can just divide this AI over 1.5 and you can start from 1. You don't have to worry about 1.5. It's taken care here. Only you have to multiply by 1 over 5 every time you get the final value. And the same thing for phase angle, goes from 0 to minus 90 for this transfer function, 0 to minus 90 for this transfer function. It has minus 45 degrees at different values. This one at corner frequency 1, at corner frequency 2. If you add them all, this is the overall phase lag for the overall system here. Okay, and since it's two systems first order series, the maximum it goes again to minus 180 degrees because it's a second order system. And so on. So you can plot transformations of all for simple proportional contour is just Kc, so the amplitude is just Kc and 0, so there's nothing to plot here. For PI controller, this is your transfer function, so you get a low asymptotic plot here and a high asymptotic plot here. Okay, this one is minus 1, low 1, and this one is moving a high asymptotic plot. The frequency again at 1 over tau I, and the phase angle from minus 90 going to 0 for a PI controller. For PD is opposite. It's going from low asymptotic plot here going to high asymptotic plot here at gradient of plus 1, corner frequency at tau d 1 over tau d, and the phase angle from 0 to plus 90. It's on positive phase angle due to the PD, which means positive phase angle means stable system. And this is the example in the textbook where how to plot the overall body plot for the whole system. This is the open loop equation here. You can see the open loop transfer function here. So we will go through this one the next class. We go one by one to plot the individual ones and then combine them in the same body plot. And the main thing is to plot the open loop transfer function. This is the open loop transfer function. This times this times this. This is the Kc 1 tau d. This is the phase lag, and this is the system here. So we'll go into that into more detail. This is given example 15.7 in the textbook, how we got overall plot, and then we will see what is being used for. What is the purpose for all this? We go into the next class, another class. The next class we'll finish off this example. Then we go into what we're going to use all this for in our control system design. Why we are doing to this a different way of approach. Instead of going to into the plus approach, this is going into the frequency domain approach, but it's got some advantage you will see later for designing controllers and even stability. and we will go into that next. Also, we can do some tutorial. You can see this clearly. We are going to just plot this on computer now. We can plot this on the log graph, but in our case here, we are not going to use the physical log graph. We can plot it using the MATLAB function, and we will discuss that on Thursday. Okay, thank you very much for today. We will stop editing. Assalamualaikum.